This is Jack Jackson, and as usual, we have a series of review problems over this entire unit. And if you're in my class, you will find that these problems are matched very closely with the Unit 4 practice tests, which in turn are extremely similar to those on the Unit 4 exam. So this should give you a good way to focus your study right before the end of the unit. So, as always, you should work the following problems on your own before moving on to the following slide to check your answers against the provided solutions. We will be working these the easiest way to work them, including using the apps built into the TI graphing calculators and my programs for the TI-84. This particular video will cover the first 5 problems on this set. So here is the first problem for you to work. I'm just going to talk about some confidence interval concepts. Describe the purpose of a confidence interval. Tell me what is the relationship between a point estimator and a confidence interval. And when we say we're 95% confident in the interval, what do we mean? So see if you can work this out. Now, when you're going to provide a little paragraph for these answers, and on the version that would be on the practice test or the exam, it might be some fill in the blanks, some multiple choice, or whatever over these same concepts. Okay, time for you to work. Press pause now. Alright, we're back now, and of course hopefully you work this out. It's very important that you take the time to actually work through these yourself so you can check and see how you're doing. So a confidence interval is an interval of values which are used to estimate some unknown population parameter, for example the population mean, proportion, or standard deviation, using information from a sample. The interval is built from the statistics from a sample, especially the corresponding sample statistic, along with the sample size and some desired level of confidence. The confidence interval will always include the point estimator, in other words, the corresponding sample statistic, which is exactly at the center of the interval, the midpoint of the interval, in the case of a confidence interval for a mean or proportion, but not necessarily for a standard deviation. The hope is that this confidence interval will contain the true population parameter. When we say we're 95% confident in the interval, what do we mean? Note that the true population parameter, for example the population mean, is some fixed number. If we were to repeat the process of constructing confidence interval with different sample means and the same margin of error, the intervals would all be the same width, but would have different centers determined by the varying sample statistics. 95% of the time, such confident intervals will contain the fixed population parameter. So, while we are 95% sure that the interval contains the true population parameter, note that it is the different intervals which are moving around, not the population parameter which is moving. Alright, how about some more confidence interval concepts? There's a three-way tug-of-war between which 3 measures related to confidence intervals? Which variables are used for these 3 things? Which of these 3 do we want to be small and which do we want to be large? What happens if we improve the size of one of these? In practice, how do we usually resolve this balance? See if you can answer these questions now. Press pause. Well, the 3 things that are in a tug-of-war are the sample size, n, lowercase n, the confidence level, which I usually call CL or 1 minus alpha, and the margin of error, which we'll call E, capital E. Which of these 3 do we want to be small and which do we want to be large? We want the confidence level to be large, which would be correspond to a small value for alpha, large confidence level. We want a small sample size and a small margin of error. Unfortunately, if we improve the size of one of the 3 values, we end up making the size of one or both of the others worse. For example, if we increase the level of confidence, then we either increase the sample size or increase the margin of error. If we decrease the margin of error, we either decrease the confidence level or increase the sample size. In practice, how do we usually resolve this balance? We typically decide on a reasonable level of confidence beforehand, often set by some standard of the field of study or the journal you might be publishing in. And then we decide on a reasonable margin of error. With these in hand, we compute a minimal sample size that will produce this balance. All right, how about some concepts about hypothesis tests? What is the purpose of a hypothesis test? Describe the null and alternative hypothesis for a one-sample hypothesis test. And what is the difference in one- and two-tailed tests? Press pause now, see if you can write out answers in a little short paragraph for each of these. Okay, well, let's see how you did. The purpose of a hypothesis test is to determine if the difference in a sample statistic and a hypothesized population parameter, or statistic from another sample in the two-sample case, is likely due to the sample coming from a different population than hypothesized, that would be rejecting the null hypothesis, or if it can be explained by normal variation within the hypothesized population, that would be failing to reject the null hypothesis. So for a one-sample test, let's describe the null and alternative hypotheses. The null hypothesis is that the sample was drawn from a population with a specified distribution. It is the status quo and is assumed unless evidence is sufficient to indicate that the alternative hypothesis is much more likely true. The null hypothesis is stated with the population parameter equal to some assumed value. The alternative hypothesis is what we're trying to prove. It is that the sample comes from a population with a different parameter. It can be stated as some type of inequality, either not equal for a two-tailed test, less than for a left-tailed test, or greater than for a right-tailed test. What's the difference in a one- and two-tailed test? In a left-tailed test, the alternative hypothesis is that the population parameter is less than that assumed in the null hypothesis. The alpha and p-value probabilities are all on the left side, so it's less than. In a right-tailed test, the alternative hypothesis is that the population parameter is greater than that assumed in the null hypothesis. The alpha and p-value probabilities are all on the right side, greater than. In a two-tailed test, the alternative hypothesis is that the population parameter is not equal to that assumed in the null hypothesis, or different than that assumed. And the alpha and p-value probabilities are split in half on each side. More hypothesis test concepts. Describe the two basic hypothesis test approaches and the decision criteria. And B, what's the difference in one sample and two sample tests? See if you can answer these with a little paragraph each. Press pause now. Well, the two basic approaches are a critical value approach and a p-value approach. Sometimes the critical value approach is called the classic method. In the critical value approach, we compare statistics. In the p-value approach, we compare probabilities. The critical value approach, a critical value, or two values, in the two-tailed case, is computed so that the probability more extreme than the critical value is alpha. So in a right-tailed test, we would have the probability to above or greater than critical value is alpha. In a left-tailed test, the probability below the critical value is alpha. If it's two-tailed test, the probability below the lower critical value is alpha over 2, and the probability above the upper one is alpha over 2. The test statistic from the sample is then computed and compared to the critical value. If the test statistic is more extreme than the critical value, it is in what we call the critical region, and we reject the null hypothesis in favor of the alternative hypothesis. If not, we fail to reject. Critical values are found with inverse probability functions and programs. In the p-value approach, we compare probabilities. We use the test statistic from the sample and compute the probability of a value as extreme or more extreme if we assume the null hypothesis is true. This probability is the p-value, p, of the test. If p is less than alpha, less than or equal to alpha, we reject the null hypothesis in favor of the alternative hypothesis. If not, we fail to reject. P-values are found with a CDF. Those are just probabilities. What's the difference in a one-sample and two-sample test? In a one-sample test, we're comparing a sample statistic against an assumed population parameter. In a two-sample test, we're comparing sample statistics, like means, from two samples against each other. In both cases, we want to see if any difference can be easily explained by normal variations, or if there's a preponderance of evidence that suggests beyond a reasonable doubt, determined by the alpha level, that the difference is due to some other special cause of variation. All right. One more hypothesis test concepts here. What are the advantages of the p-value approach over the critical value approach? What is a p-value? And when using the p-value approach, what is the decision criteria? Some of this we already have done, but pause and do this yourself now. Once a p-value has been computed and reported, the reader can easily compare it to any desired alpha value without doing any further calculations. The size of the p-value also gives an indication of how strong the evidence is for rejecting the null hypothesis. The calculator wizards app programs in the calculator and my programs also produce p-values, so this method is easier with a graphing calculator. What is a p-value? A p-value is the probability of getting a sample with a sample statistic at or more extreme than the one we actually obtained. If we actually reject the null hypothesis, then the p-value is the probability of a type 1 error if we only reject for statistics the same as or more unusual than the one we actually obtained. When using the p-value approach, what is the decision criteria? We compare probabilities, the p-value, to alpha. If p is less than or equal to alpha, we reject the null hypothesis in favor of the alternative hypothesis, and there is enough evidence to conclude that the alternative hypothesis is true. If p is greater than alpha, then we fail to reject the null hypothesis, and the evidence presented is not strong enough to claim that the null hypothesis is false. Let's do another one. Hypothesis test concepts. Describe the 4 possible outcomes of a hypothesis test. There are 4 outcomes. The null hypothesis is true. The alternative hypothesis is true. We reject the null hypothesis, or we fail to reject the null hypothesis. If the intersection of those gives us 4 possibilities. A type 1 error is when the null hypothesis is true and we reject it. A type B correct conclusion is when the null hypothesis is true but we fail to reject it. The alternative hypothesis is true and we reject the null hypothesis is called a type A correct conclusion. If the alternative hypothesis is true and we fail to reject the null hypothesis, that's a type 2 error. Notice if we fail to reject the null hypothesis, we could only have made a type B correct conclusion or a type 2 error. If we reject the null hypothesis, we can only have made a type 1 correct conclusion or a type 1 error. If the null hypothesis is actually true, we either made a type 1 error or type B correct conclusion. And if the alternative hypothesis is true, then we could have only made a type A correct conclusion or a type 2 error. I've also put on here our justice system analogy to put for comparison. Remember, in the justice system analogy or courtroom analogy, the null hypothesis is that the defendant is actually innocent, or it's at least innocent until proven guilty. So we assume innocence. That's the null hypothesis. So if the null hypothesis is true, the defendant is actually innocent. If its alternative is true, then the defendant's actually guilty. A verdict of guilty would be rejecting the null hypothesis. A verdict of not guilty would be failing to reject the null hypothesis. A type 1 error, then, is when an innocent defendant is convicted. That is, rejecting the null hypothesis when the null hypothesis is actually true. The other type of error is a type 2 error. That's when a guilty defendant is acquitted. They get a not guilty verdict when they really did do the crime. That's a type 2 error. Type A correct conclusion would be the guilty defendant is convicted. That is rejecting the null hypothesis when the alternative really is true. The other good thing that could happen is if we fail to reject the null hypothesis when it is actually, when the null hypothesis is actually true. That would be like an innocent defendant getting acquitted. Describe the conditional probabilities associated with each of these 4 possible outcomes of a hypothesis test. Well, the type 2 errors are type 1 error, which has a probability of alpha, and a type 2 error, which has a probability of beta. Alpha is the probability of type 1 error. That is a conditional probability, the probability that we reject the null hypothesis given that the null hypothesis is true. For our justice system thing, that would be the probability the defendant is convicted given that the defendant is innocent. The type 2 error has a probability beta. That's failing to reject the null hypothesis given that the null hypothesis is false. In our example, that is the probability of a defendant being acquitted given that the defendant is actually guilty. We want alpha and beta to both be small, but what we do typically is we control alpha in our process, in our hypothesis tests and confidence intervals. The complementary probability to alpha is 1 minus alpha. That's the probability of a type B correct conclusion. Again, all 4 of these are conditional probabilities. This one is the probability that we fail to reject the null hypothesis given that the null hypothesis is true. For example, probability that the defendant is acquitted given that the defendant is innocent. And the 1 minus beta is the probability of a type A correct conclusion. That's the probability to reject the null hypothesis given that the null hypothesis is false. Probably the defendant is convicted given that the defendant is actually guilty, for example. Come back for the next video for a few more questions worked out.